Some of you asked me about some special cases that follow when the function is conservative when we did line integrals and Green's theorem. To remind you, we did a remark about what we call multi-connected domains. In talking about integrals, curve integrals, when we talk about the Green's theorem, a theorem like Green's theorem, conservative functions, all these things, remember we always said something all the time. We always said if f is smooth on and inside a curve C, a closed curve, of course. What did we mean by on and inside a closed curve C? In general, we mean a closed curve like this, okay? And when we say on and inside, this is the inside. Of course, the mathematical word is not inside. The math word for this region is the interior. Okay, and this is the curve C. We have too much details about simply connected domains, multi-connected domains, simple curves, closed curves. But we don't want to go deep into these concepts. Rather, I like in this video, because some of you asked me about it, I like to explain two things, basically. The first thing, if f is conservative, why do we have the integral from AB f to dr equals f of b minus f of a? Remember, little f being the potential, so its gradient is big F. This is the first thing I like to explain today. The second thing that I like to explain is we had something about multi-connected. So what do we mean by multi-connected domains? We had a remark in a class that if you have a closed curve like this called C1, let's say, and you have another closed curve inside it, C2, and if the function is conservative and smooth between the two curves. I remember we use this idea to isolate. So usually what happens is, okay, we have a problem, so let's make it a little bit bigger, okay. So we have a problem here. We isolate it somehow using the red curve. Then we say, okay, maybe integrating over the red curve is easier than the blue curve. So instead of doing the integral on the blue curve, let's do it on the red curve. This was the idea. And I like here just to remind you here that in this case, if f is conservative, it is very important that conservative means there's a little f whose gradient is big F. And if f is smooth in the green region, then what's my conclusion? My conclusion is that the integral over C1 f dot dr is equal to the integral over C2 f dot dr. Of course, oriented, both curves must be oriented in the same orientation. So if we take, for example, this orientation for this curve, we have to take the same orientation for the second curve. Okay, so this was this remark. Before explaining the stuff that I want to explain, quickly, I want to remind you of one example that we needed this remark to solve. So if you remember, so quickly, for example, if we take the function, if we have the function minus y over x squared plus y squared, x over x squared, y squared. It's very easy to check that the derivative f1 with respect to y is equal to derivative f2 with respect to x. So this is what we use to say that f is conservative. It's very easy, just differentiate the first and the second. We did this in class. Okay, again, I just want to remind you why we need this remark, this last remark, the integral over C1 is equal to the integral over C2. Okay, but in this example, if we look at this function and we look at the denominator is x squared plus y squared. This x squared plus y squared is not defined. It's not defined at the origin. So if you substitute x0, y0, you have a problem. So my function here is not, so f is not smooth at the origin. So if you talk about any region that contains the origin, so for example, if you take the unit circle, okay, and I'm not taking the unit circle, instead, if you take any circle, so if this was x squared plus y squared equals r squared, so if you take a curve, if C is a circle of radius r, of course centered at 0, 0. In this case, okay, in this case, is f conservative? It is conservative, but it's not smooth at a point inside the curve. Okay, so remember, if the function is conservative and smooth inside in the interior of the curve, then the integral over closed curve is 0. So in this case, because f is not because f is not smooth, so since f is not smooth inside C, we can't say that the integral over C f to dr equals 0. Let's take this orientation. So we write this, okay? Remember, this circle on the integral means that the interior is to the left. In these cases, when we have a closed curve like this, it is the counterclockwise orientation. Okay. So in this case, I can't say, although the function is conservative, I can't say the integral is 0. So how do we do this integral? This means we must do it using parameterization. So we must use the parameterization. What's a parameterization for this curve? It's cosine t, sine t. Of course, t is between 0 and 2 pi. Again, the 2 pi, you have the choice. You can include it or not. It's your choice. It's not a big deal, I mean. Okay, so what's the integral over C? Now, this parameterization is valid for the unit circle. If you're dealing with an arbitrary circle of radius r, like our example, we just multiply it with r. So you can multiply the r outside, you can include the r inside. This is my parameterization. So to guarantee that the x squared, this is the equation, x squared plus y squared is r squared. So now if you use this parameterization, so you substitute this parameterization into f. Now what happens when you substitute this parameterization? You go back to f, so this is f. Down in the denominator, you have x squared plus y squared, that's r squared. So in the x and in the y, the x coordinate and the y coordinate, the denominator is, okay, so for both x and y, the denominator is r squared. For the numerator, in the x coordinate, it's minus y, so that's minus r sine t. In the y, it's x, which is r cosine t. This is dot r prime. What is r prime? It's minus r sine t, r cosine t, dt. Now, if you do these easy computations, it will be r square sine square t plus r square cosine square t over r square dt. Now nicely, the r square gets cancelled, sine square plus cosine square is 1, and the final answer is 2 pi. So in this example, this is a very nice example because it provides you a case where the function is conservative, yet the integral over a closed curve is not 0. And the reason for that is the function is not smooth. You have a problem inside the curve. This is the point 0, 0, the origin. Okay, so if you do the integral over any circle of radius r, you get the answer 2 pi. Now again, remember what is my target in this example. I want to explain this scenario. So now imagine in the same example, so for the same function, imagine you have a curve like this, an arbitrary curve. So this is the idea, okay? This is the idea. You are going this way. And you want to find the integral, so this is your c, you want to find the integral over c f dot dr. Now, the function is conservative, yes, but still we still have the same problem inside this curve. We still have the point 0, 0 inside. So this is where this idea becomes useful. You say, okay, I have my curve, this outside, okay, the outer curve. I have this curve. Inside it, I have a problem, but let's isolate the problem. So I have this green curve. Inside it, I have a problem. Let's isolate it. How do you isolate it? You draw another easy closed curve that you can easily deal with. For example, the circle. And why did we choose the circle? Because we just did the circle. If you choose any circle about the origin, the integral in the end is going to be 2 pi. So now you ask, is my function smooth between the two curves? Yes, it is, because you isolated the origin. By drawing the straight curve, the origin is no longer in your interior. So now I can say, okay, instead of doing the integral over this green curve, I can do it over a small circle of radius r. Now what is r? It is very small, just to guarantee that the red curve is inside the green curve. And we just did the computations, and the answer is 2 pi. This is where this idea becomes really useful, okay? Okay, so this is the example that I wanted to show you. Now, away from the example, let's go back to the first page. So I want to explain these two things. The first thing, why, if the function is conservative, so that there is a little f whose gradient is big F, why do we have this formula? And then how do we get these two integrals equal? Okay, so I want to explain the case, this one, okay? Why do we have gradient f? Because that's the meaning of the integral of f here, where gradient f is equal to big F. So basically you just replace big F by the gradient. Let's see why this is true. And for us, we can take the big F as F1, F2. So gradient F is just 2 coordinates. So I'm dealing with 2 coordinates. It's very similar. If you're dealing with 3 coordinates, it's very similar. Okay, so basically, when you say the integral from A to B, gradient f dot dr, what is that? That's the integral. Gradient f is just 2 coordinates. It's f differentiated with respect to x, f differentiated with respect to y, dot dr. So you have a curve. This is your curve, okay? You're doing the integral from A to B. This curve has a certain parameterization, okay? And t is, let's say, between alpha and beta. Okay, now how do you compute the integral? So imagine you have values for this function. You have this clear parameterization. You take the parameterization and you substitute it into your function. So basically, what does this become? This becomes the integral. So the first coordinate, yes, it is f sub x, but you substitute the parameterization. And the same, sorry, this is little f sub y, you substitute the parameterization. Dot what? Dot r prime of t. Now what is r prime of t? R prime of t is x prime of t, y prime of t, because remember, the parameterization has 2 coordinates. If you're dealing with a curve again in R2, you have just 2 coordinates. And what are the t values? These are from alpha to beta. Now if you do the dot product, what is it? So this becomes this becomes the integral from alpha to beta f sub x of r of t times x prime of t plus f sub y of r of t, of course, times y prime of t, all of this dt. Okay? Now we look at this quantity. To make the idea clear, I want here to explain what I'm going to do there. So this is just for explanation. Imagine, just to make it very, very clear, imagine you have a function, and this function is a function of two variables. So imagine you have f of xy, let's say equals x squared plus y cubed. At the same time, imagine that x is a certain quantity in terms of t, and y is a certain quantity in terms of t. Okay, don't say x is t squared because here you have square, so let's change this to t to the 30. These numbers are just random numbers. Okay, so the x and y, those together, they are making r of t. So r of t here is like t squared and t to the 30. Just imagine it this way. Notice that in the end, if you go back to f, I can say this is a function of t. How? Because if you replace x by its value in t, you will have t squared plus the y is t to the 30, y cubed is like this. So in the end, you have it in terms of t. Now if I ask you, how do you differentiate it with respect to t? Just differentiate it like calculus. You take the 2 down, t squared times 2t, plus the 3 down, t to the 32 times 30, t to the 29, right? Now what is this exactly? This is 2, what is this? T squared is x. What is 2t? Is x prime of t, plus 3, this is y squared, and this is y prime of t, right? So basically this is like, what is the 2x? The 2x is simply, yes, it is f sub x times x prime of t plus f sub y, if you differentiate this function, times y prime of t. And this quantity, if you compare it, this is exactly what you have here, right? This is exactly it is. So what happens here? What happens here in general? Remember, you had this, what we call is the chain rule. You had it in calculus 3. So imagine you have a function f. This function f depends on x and y, but then x depends on t, y depends on t. This is exactly what we have. The original function is a function in terms of x and y. The curve has a parameterization in which x depends on t and y depends on t. So in the end, I can look at f as a function of t. If it's a function of t, what is f prime of t? It is f sub x, x prime of t, plus f sub y, y prime of t. This is exactly what we have. So now going back to our integral, this integral from alpha to beta, this quantity, the integrand, is nothing but, yes, it is f prime of t. It is exactly what we have there. It is this identity exactly. It is f prime of t. And what's the integral of f prime of t? It is f of t. But it's not, it's in our case, it's not f prime of t. Rather, I like to write it as, I rather write it as d by dt f of r of t. Right? It's the same thing. So now what's the integral dt? It is just f of r of t. Okay, and the limits are from alpha to beta. So this becomes, I can delete this now, I think. Okay, so this is f of r of beta minus f of r of alpha. But what is r of beta and r of alpha? Remember, what is r in the beginning? You had a curve C that starts at a point A, ends at a point B, and it has a certain parameterization where t is between alpha and beta. But when we say a parameterization, that means every value of t from alpha to beta gives you a certain point. When t is alpha, you must get this point. When t is beta, you get that point. So basically, r of beta is the point B, r of alpha is the point A. So this is simply how we obtained this formula here. So remember again, we did this formula in class. This is the proof, let's say. Of course, in these proofs, we must assume a smoothness of f, that we don't have any problems. We always assume this stuff. Okay, so this is the first part of this video that I like to show you. The second part, again, some of you asked me about the second remark, why if we have two curves, concentric curves like this, and if the function was smooth and conservative between them, why do we have the two integrals equal? So I want to explain the case when the integral over C1 is equal to the integral over C2, of course, in the same orientation. This is when f is conservative and smooth between C1 and C2. Of course, here we need to explain it graphically. So this is like the curve C1 going this way, for example. Then inside it, you have another curve, C2. When we say the function is smooth between them, this is what we mean between them. Okay, so you don't have any problem. Again, if you have problems, we isolate them like we did before with the circle using the C2. We want to see why, in this case, the integral over C1 is equal to the integral over C2. The idea somehow is like this. So if you fix a point, just fix a point here on this curve, call it A, move all the way on C1, okay, until you get back to A. Then when you get back to A, move this way to C2, move this way until you get back to this point. Then let's do it using another killer. So after moving over C2 and you reach this point, go back to the same point A. So basically, the parallel, if you followed me, the parallel curve C is a closed curve that starts and ends at A. So in this case, the integral over the parallel curve is equal to 0. Why is it equal to 0? Because the function is conservative and is smooth in the interior of that curve. Now in this case, what is the interior of that curve? It is the green curve. So basically the idea is the two curves are making one curve for you. So what is C? Now if you write the details, what is the C? The C, you started from A, you moved all the way over C1 until you get back to A. So this is C1. Then you moved on this part of the curve, you moved here, like this, right? You moved over this curve. So I'm calling this from A, if I call this point B. So then you moved from A to B over that brown line segment, f dot dr. Then you moved over the the red curve all the way back to B. This is what? This is C2. But now, for this C2, when we talk about the interior of the curve, the interior has to be to the left of a traveler. Now this is the interior, okay? For the total curve C, the interior is the green region, which means when you move over the red curve, you have to do it the other way. That's why we multiply with a negative sign, because for this, I don't want to add more arrows on these complicated curves already. But again, quickly, if this is C1 and inside it you have C2, this is the interior. On the outer curve, to have the interior to the left, you have moved this way. But for the other one, you have to move the other way. okay, to guarantee that the interior is to the left. This is how we must do it. So for the interior curve, for the C2, we must multiply with negative to guarantee that the interior is to the left. Then plus what? I'm going back. So remember, I am writing the curve C that started at A and ended at A in a strange way. In the beginning, we moved all the way over C1. Then we moved all this brown line segment from A to B, then over C2. Then I'm moving back from B to A over the brown curve in the other way, f.dr. All of this has to be equal to 0. But in this case, we know the relation between AB f.dr over the brown curve, the same integral, but in the opposite direction. So they get cancelled, AB with BA, because we're doing it over the same curve, the same line segment. They get cancelled. And then if you move the integral minus C2, you get the integral over C1 is equal to the integral over C2. And this is the proof why if we have a multi-connected, so this is called multi-connected domain, because you have multi-regions. Again, this concept has some details in it. We don't want to go deep there, but if you have a multi-connected domain, that's what happens. And this is the proof. Remember the benefit of this remark. It's not theoretical only, but we needed it, for example, in solving this example when we had an arbitrary curve to allow you to replace complicated curves